Okay. All right. So I just wrote this stuff down. Just wanted to point out that when we find the best surface, it kind of looks like we're doing linear regression, right? Because you want to find the best line that fits through all the points, but doing principal components analysis and doing linear regression are not the same thing. I just want to make sure I point that out. They're not actually the same thing. They look artificially the same, but you're solving two completely different problems, okay? So what linear regression does is that what you're doing is you're trying to find the line of best fit between all the points that minimizes the sum of squared errors. So what you're doing is you're finding the error between the predicted result and the expected result. With linear regression, you have expected outputs. Okay, with principal components analysis, we have no expected outputs. We just have a bunch of data. We don't know what the labels are. We just have data. Right? So PCA, what it does is that it finds the best surface that minimizes projection errors. So minimizing sum of squared errors and minimizing projection errors are two completely different things. Even though they may look the same, they're actually not. Okay? So for example, we have linear regression here. We want to find the line, and then the sum of squared errors is finding the distance between the example and the predicted output. You're going straight down. So this is what the sum of squared errors is, because you're finding the difference between the predicted value, which is along the line, with the expected result, which is either above and below. Okay, so that's what linear regression is. And for PCA, what you do is you're finding the projection error, which is the perpendicular distance from the example down to the line. You want to find the projection error. So the sum of squared errors and the projection error, those are two completely different error metrics and thus resulting in two completely different problems. So they're actually not related at all, so don't get them confused. Okay? So let me just continue. All right, so PCA transforms the data, right, from, we have some example that is within the space of n features, to a new example that is reduced to a set of p features instead, right? So we're going to reduce from n down to p, okay? So Zi is transformed, or so Zi is the transformed example using axes, you know, U1, U2, up to U, P, sorry. I can't. Usually towards the end it's kind of screws up. That's okay. Okay, there we go. Okay? Okay, so we calculate PCA by doing what's known as singular value decomposition. So we do this by performing singular value decomposition. Okay, or SVD for short. Okay? So before we actually compute the singular value decomposition, what you have to do is we need to compute the covariance matrix first of your actual data set. Okay, so before we cover SVD, we need to compute the covariance matrix. Oh, I'd just like to point out right now that I'm not expecting you to compute PCA or SVD for the exam. I'm using this so that you can do this in the next lab. So there are actually functions that will do this for you. I just want you to be able to practice that in the lab. But the actual exam itself, I'm not expecting you to do this because it's actually quite computationally intensive, and I'm not expecting you to do that. Okay, so before we cover SVD, we have to compute what's known as the covariance matrix. Okay, so given a data matrix, right? Just recalling from before, of size m by n, and the data matrix is stored in X, right? Where this is the number of examples, and this is the number of features. Okay. Okay, that's great. Okay, so to compute this, it's called sigma, and it looks like this matrix. So along the diagonals, we compute the variance of each feature squared, and then along the off diagonals, we compute what's known as the covariance. This is 1, 2, 1, 3, 1n, and 1, and 2, and so on. Okay, just to recall, if you want to compute the variance of a particular feature, all you have to do is sum over the square differences with the mean. So this is J. Let's see here. Not J. Let's do K. Let's do K. 1, 2, M, and then. Okay. So that will be defined as the variance. That's fine. And if you want to calculate the covariance, it's a related formula. I'm not expecting you to compute this for the exam. It's fine. So what you want to do is you want to calculate the products of the differences between each feature with the example and the corresponding mean. Okay, just notation. I just want to put that there just for completeness. Okay, so if you actually mean normalize, as we talked about, what you can do is you can actually compute the covariance matrix using very simple matrix multiplication. Okay, so if we mean normalize x, right? The features of x. Okay. We can calculate sigma by matrix multiplication. Okay, so what you can do is you just do this. Okay, and that's how you do it. And I can show you if you wish, but we can certainly show it. Okay, so this is our, data matrix where we have, first example, all the features for the first example defined in the row, and then the second example, okay, down to the last example. Okay, and then make sure that this is mean normalized. Okay, if you were to transpose this and multiply it with itself, you'll actually, if you can work it out yourself, if you took the transpose and multiplied it by itself, you will actually see that it is calculating the covariance matrix for each feature that we have once you mean subtract or mean normalize the actual matrix. Okay, so we perform PCA on the covariance matrix, right? So I'm sorry, we perform PCA by finding the singular value decomposition of the covariance. Sorry. Okay? So what exactly is the SVD? What does it actually do? What the singular value decomposition algorithm does is that it takes a matrix and it decomposes it into a product of 3 matrices. Okay? So SVD decomposes a matrix into a product of 3 matrices. Okay, so it takes X, right, and it decomposes into a product of U, S, and V transpose. Okay, so this is a matrix of size. So we know this is going to be M by N. This U matrix is a size M by M. This is a matrix of size M by N, and this is a matrix of size N by N. Okay, you can represent it as a product of 3 matrices, and what U is, it consists of the orthonormal eigenvectors of X transpose X. And I'll talk about all this notation in a little bit. I'm not expecting you to compute eigenvalues and eigenvectors in this course. It's not the focus here. I just want to give you enough theory to know what SVD is so you can learn it in practice, so you can use it in practice. S contains what are known as the singular values of X in a diagonal matrix. Okay? And V also consists of the orthonormal vectors, but instead of X transpose X, it's XX transpose. So it's simply this. Okay? In practice, these are what are known as the left singular vectors, and this is known as the right singular vectors because of the switch of the transpose. All right? So how do you compute the SVD? Very simple. There's one MATLAB command to do it, which is called SVD, and it outputs 3 matrices, U, S, and V, and that's all you have to do. Okay? I'm not expecting you to compute this in this class. You're going to use that for the next lab. Okay, so how to compute SVD. Very simple. The MATLAB command is called SVD, which returns three matrices, U, S, and V, and you just put in whatever matrix you want. Okay? So we'll call this sigma, and then what you have to do is you're performing SVD on the actual covariance matrix. So this is covariance matrix. You're doing it on the covariance matrix. But in general, you can do it for any matrix you want. Okay, so I have these two things that you may or may not remember. It's the concept of orthonormal and the concept of eigenvectors. Okay, so what exactly does orthonormal mean? What orthonormal means is that you have two vectors that are not only perpendicular to each other, but they both have a length of 1. They're normalized to a length of 1. Orthonormal. Okay, so what is orthonormal? Normal. Okay? What that means is that there are vectors that are perpendicular to each other and have a length of 1. Or the magnitude is 1, whichever notation you wish to adopt. Okay? So that's what orthonormal means. Very simple definition. Okay. So that's orthonormal. What is an eigenvector? I'm just going to give you a very bare bones definition. I'm not going to ask you to compute that in this course. Okay? So what an eigenvector is that it is a vector such that when you take this vector and do a matrix multiplication, do a matrix vector multiplication, it's exactly the same result as taking this vector and scaling by a certain amount. Okay? So it is a vector where if we multiply this with a matrix, you get the same result as simply scaling it. Okay? So what I mean by this particularly is you have some matrix A, you have some vector x. It's the same thing as taking this vector x and multiplying it by some scalar, which is lambda. All right? So this here is a m by m matrix. So it's usually, it only exists for square matrices. I'd like to point that out. So let's see here. So only for square matrices. That's why you have to, when you're doing the PC and all that, you have to multiply with the transpose in order to make it square. But, you know, that's just a little fact that doesn't need to be known. So this is m by m, okay? This is an m by 1 vector, and this is also m by 1, and this is just a scalar. Okay? So the scalar value that is found to satisfy this relationship is called an eigenvalue. And the vector associated with the scale is called an eigenvector. All right? So the scalar lambda, to make this work, is called an eigenvalue. Okay? And the associated vector is called an eigenvector. That's all I'm going to mention. There's nothing further to discuss there. Okay? Oh, actually, one last point. Eigenvectors are not unique. Okay? If you take this eigenvector and if you scale up by a certain amount, or if you change the sign, it is still technically an eigenvector because you're still multiplying by a certain scale, right? So eigenvectors are not unique. Change the sign or scale it, it's still an eigenvector. Just wanted to point that out. Still an eigenvector. It's just a property. Okay, so that's all I'm going to talk about for eigenvector. I just wanted to establish that notation because people may not remember what an eigenvector is, and that's all I want to talk about. So there are some properties for U and V. U and V are defined as orthonormal matrices. Okay, so what I mean by orthonormal is that each of the columns, the magnitude is 1, and also when you take that matrix and multiply by its transpose, it's equal to the identity matrix. So this means that each of the columns have a magnitude of 1. Okay? Each column is perpendicular to the other columns. Okay? And also one last point. This also implies that when you take the transpose and multiply by itself, it's equal to the identity matrix. The identity matrix is just a diagonal matrix where everything is 1s except for the off diagonal. All the diagonals are 1 and everything else is 0. Okay? Also, this implies that it's the identity as well. And also, this implies that the inverse is simply the transpose, which is nice. So we'll use this later. If you take the matrix and multiply by its transpose, if that's equal to the identity, then the inverse is also equal to its transpose. Okay, that's cool. Okay, almost done here. All right, so let me see here. So what happens is that U and V places their eigenvectors, their orthonormal eigenvectors, in columns of this matrix. So U and V place their orthonormal eigenvectors in each column. Okay? So what this means is that you have U and then it looks like this. Okay? So you have the first column, right? That's the first eigenvector, second column, and then you keep going to the end, and there are m of these, because this is a size m by m matrix. Okay? With V, it's pretty much the same thing, but there are n of them instead, because it's an n by n matrix. So V1, so you have another eigenvector here, all the way up to n. It's n eigenvectors. Okay, that's cool. All right, so I talked about U, I talked about V. I haven't talked about the matrix S yet, and that's a very special one, which we'll talk about soon. Or we'll talk about later, but I'll just give you some bare bones definitions now. So S contains the square roots of the eigenvalues for the eigenvectors of both U and V. So it's actually cool. So these eigenvalues actually are shared between both U and V, which makes it a pretty unique decomposition. These for the eigenvectors shared between U and V. Okay? So what it looks like, as I talked about, it's a diagonal matrix. So it looks like this. So you have S11, S22, all the way down to, down like that. So let me just make one more just to be clear. Okay, and the rest are zeros. So it's a diagonal matrix. Okay. Also, what I'd like to point out is these are what's known as singular values. So these are singular values. And usually the decomposition provides them in decreasing order. So the largest singular value is going to be at the very top left, and then it starts to decrease as you go along the diagonal. So the singular values, and they're sorted in decreasing order. So what I mean to say is that the first one is larger than the second one, and the second one is larger than the third one, and so on and so forth. Okay? All right. Okay. So here's some properties with the PC, and now that I've covered this theory here, talking about this stuff. So when we talk about when you do the PCA, you're applying it on the covariance matrices. So if you apply the SVD on the covariance matrix, you actually are able to get the principal axes immediately. All right? So we apply SVD to the covariance matrix to perform PCA. Okay? And here are some properties. I'm not going to prove this. It actually will take a very long time, and I don't want to do that. I want you to just use this immediately. Okay? So when you perform the SVD on the covariance matrix, when you take a look at the matrix V, each column of the matrix V will actually give you what the principal axes are for your data. All right? So the principal axes of of the PCA is defined as the columns of V. Okay? And I talked about each column is orthonormal to all the other columns. So if this is V, right? Okay, basically this defines the first axis, U1, right? This defines the second axis, U2, and then they're up to n of them. Okay? So what each column does is that it tells you how to project each example onto that new axis. So the first column, what it'll tell you, it'll give you a recipe on how to take the first feature, or it's not first feature, it'll actually tell you how to take your data and transform it into the new first feature. And then the second column will give you a recipe that'll take your training example and transform it so that it is a point on the second feature of the newly transformed data, and so on and so forth. Okay? So each column tells you how to project each example onto a new axis, okay? Where each column is defined as a new axis. Okay? So specifically, if I wanted to compute my new data points, right? So for example, if I wanted to compute this one for a particular training example, what you're going to do is you're going to simply take a dot product with the first column with your training example. So you do U1 transpose times x of I. Okay? So that'll be the first feature of the new axis, right? So this is there'll be a 1 by m when you transpose it, and this will be an m by 1. So when you compute that, you get just a single value. And then if you want to compute the next feature, right, to be projected onto the new axis, you take the second column and just multiply it with your example here, and that goes. And then you keep going up into as many as you want. All right? So you keep going up into, z of n, right? Right, and this is sorry, k. But we go up to as many as we want. Okay? So we want to reduce this. So you can kind of see where we're going here. Okay? So this will be the procedure. So if you want to take your data, and if you want to reduce it down to p dimensions, all you have to do is just sample the first p columns of V and do a dot product with each example with each column in order to be able to produce a new feature vector that will reduce this down to p dimensions. Okay, so that's basically the procedure that you do. Okay, so the new example, okay, which is z of I, where it's, first feature, second feature, up until as many dimensions as you want. Z of n, sorry, I screwed that up. This should be Z P of I. Sorry, made a little screw up there. Okay, the new example, that, right? So this is transformed into p dimensions. The new example here is created by finding the dot product of each example with the first p columns. Okay? So if you want to reduce your data down to 2 dimensions, all you have to do is just take the dot product with your example with the first 2 columns. And the first column will give you the map, the projected point with the first axis, and the second column will give you the projected point onto the second axis. And you can retain as many as you want. It doesn't have to be 2, it could be 3 or 4, it doesn't matter. Okay, so doing all these dot products is a little computationally intensive. So what you can do instead is you can do this by pure matrix multiplication instead. So to do this efficiently, okay, let's call Vk to be the matrix V with only the first, not k, let's call this p. First p dimensions, or p columns. Okay? So if you want to compute your new set of features, therefore you would just do, let's call this Z is equal to X VP. Okay, so that's how you calculate it. Very simple. Okay? So what this does is that if you have each example in a row, what you do is you take your data matrix, which is mean normalized, by the way, and if you multiply this by the V matrix with the first P columns, what this will do is that it will give you a dimensionally reduced data set where each row is the new example projected onto the new axes. All right? So I like to point out that this is mean normalized. Okay? And then this would be a N by P matrix. Okay? And this would be an M by N matrix. Okay? And then what this will produce is an M by P matrix. And what this will do is that each row of Z is the example projected onto the new axes. And that's seriously it. It's just a basic matrix multiplication. Okay, so I talked about going down. Okay, but let's say we want to do the reverse step. Let's say we want to go backwards. Supposing we have this data that was, you can consider this as a data compression, right? Where we eliminate a bunch of dimensions to go down to a reduced set of features. But let's say we want to go backwards. Let's say we have this data matrix of reduced features, and we want to go backwards and try to reconstruct what the original data was. Well, you can't do that because what's happening is that when you are finding this new service, you're trying to minimize the projection error. So because that projection error is still there, you can't quite exactly go back to the original data set, but you can go back to what it would best look like. You know, it's the best reconstruction possible, but to minimize the projection error, but you can't go back and actually create the original data set unless you keep all of the actual features, which is kind of pointless, right? So here's my last point, and then I'll let you guys go. This is data reconstruction. Actually, I've got this and then the number of, that and then number of principal components and we're done. So data reconstruction. Okay, data reconstruction. So suppose we have reduced our data down to P features. Okay, so let's say we've got that, all right? Because of the projection error, there's no way to actually go back to the original data unless you actually use all the features, which kind of eliminates the purpose of dimensionality reduction. But, you know, I just want to put that in. Because there is projection error, inevitably there will be. Projection error, not projective. There's no way we can go back to the original data. But we can reconstruct what it may look like to the best of our ability, but we'll never go back to the original data. But we can, you know, reconstruct it to the best of our ability to the original data. Okay? So what we can do is we can approximate it. We can, however, approximate. Okay? We can, however, approximate the data. So this is actually commonly used in data compression. So let's say you have a bunch of data and you want to compress it down to a set of P features, right? And let's say you wanted to take a look at what the original data may have been. So this is what's known as data reconstruction, where you have a reduced set of features that'll save you space. What would the original data look like? What should have it look like if, you know, we have these features and we want to go back to the original N features? How would it look like? You know, how could we approximate what it would have looked like? Okay, so this is commonly used in data compression because all you have to do is just, instead of transmitting the full matrix, you would just translate, you would just transmit the, you know, the reduced set of features, right? So this is commonly used in data compression. So the SVD and the PCA and stuff, it's actually used quite a lot in data compression. Okay, where only P features are used instead of the full N. Okay, so let me just give you a graphical example. So the whole point of the PCA was to find the surface with the minimal projection error, right? So we had something like this. So here's a recall. Let's go from 2D to 1D. Almost done, don't worry guys. So this was this surface, right? And we wanted to minimize the projection errors, right? And then we originally had, so when you do this, we get this axis. I'll call this U1, I guess, just to be consistent, right? Where it may look something like this. Okay? So we want to go from here to here, right? So, this is what we're given. Now, what we're saying here is that we're now given this representation, this just single line. How do we go back and reconstruct the data so it kind of looked like the original, what it looked like before we actually did anything? So we're given this now. How do we go back? Well, what you can do is we have this surface that was defined. So what you do is you basically project these points back onto the surface. So if you wanted to do that, then it's going to look something like this, maybe. So you have, this here, right? So you go back here, and then this is the line of, this is the projection error. So what would happen is that you would map these points back onto where it would fit on the line. So like this, right? So these were the points that minimize the projection error. So this is what the approximated reconstruction looks like. So that's what it would look like. Okay, so the more features that you have, the more you'll be able to reconstruct what your original data looked like. So that's what it is. So it's actually quite easy to do it. It's just another matrix multiplication. So if we had this, Z was X times VP, okay? And remember, this is mean normalized. Okay? How do I get this guy? How do I get that? Well, it's pretty simple. All you have to do is just multiply by the inverse of VP, right? So therefore, Z, X would be equal to Z VP inverse. But we also know that this matrix is orthonormal. So it's actually just Z VP transpose. Okay? Because this is orthonormal. Okay, and I'm going to call this hat X here. So what this is that this is the reconstructed data. Okay? And all you have to do is just take your projected data and multiply by the transpose of VP. Okay, so this is VP transpose. And that's how you do it. Okay? So this is reconstructed data, but I'd also like to point out that this is mean normalized. Okay? If you want to actually complete the reconstruction, what you have to do is you have to go through every single row of this matrix and add back the means that were subtracted on top. All right? So to go back to the original data, okay, you add the mean of each feature on top of each example. Okay, so the final reconstruction will look like this. So I'm going to call this X tilde, which is the reconstructed final data. Okay, so this becomes, you take, actually no, let me just move this to the side, cut this. So if this was my reconstructed data without the mean, it's got a bunch of vectors here, right? So each row is a reconstructed example without the mean, right? Okay, if I want to get the final reconstruction, all you have to do is just take each of these rows and add the mean on top, the mean of each feature on top. And so on and so forth. Okay? And this mu here is the mean of each feature. Okay? So mu would be, mu1, mu2, and up to as many features as we have. So Okay? And if you recall, the mean of each feature is just, let me see here, it's 1 to m of, actually no, sorry, x. Okay, that's just finding the mean of each feature. So you actually would compute that beforehand anyway. So that's how you'd reconstruct your data. Okay, so what you do is if you're given your, your compressed or your projected data, all you have to do is just multiply by the transpose of the V matrix for the first P columns. And then once you have that matrix, just to every row, add the mean of every feature to get your reconstructed result. And that'll actually be part of the last lab. It's actually very simple to do. Okay, I've got one last point to cover. Shouldn't take more than a couple of minutes. One thing I haven't covered yet is, how many columns, how many axes do you choose? Like, we go from 3D to 2D or from, 10,000 to 20, but how many axes or how many dimensions do you ultimately choose in the end? How many principal components or how many principal axes do you actually choose? I haven't talked about that yet, and that'll be the last topic that we cover here. Okay, so last question. I guarantee you this shouldn't take more than hopefully a few minutes, and that's all we got time for. Last question. How many principal axes do we choose? What components do we choose? What's the guideline here? There are some simple heuristics that actually do work in practice, and I'll cover that now, right? So what we do is we haven't taken a look at what the singular matrix X is, and I'm going to talk about that now. So each value in the singular matrix, okay, of the PCA tells you how much variability each axis gives in your data, in your projected data. Axis gives in the data. Okay? So the larger the variability, the larger that axis would contribute to the data's behavior. So what you want to do is you want to capture as many principal components as you have that will explain the behavior of most of your data, and then you can discard the other principal components. All right? So the larger the variability, the larger the axis contributes to the data, contributes to the data's behavior. Okay? So the more axes you keep, the more variance that is retained for your data. Okay? So the more axes you keep, the more variance that is retained. The more variance is more variance that is retained. Okay? In a lot of statistics books and a lot of data science books, this is what is known as the variance explained. So you want to capture as much data as a certain percentage of the variance being explained in the data. Okay, so this is called variance explained. Okay, that's what you see in literature, variance explained. Okay, so basically how much each axis explains the variance in the data. Because the singular values are ordered from increasing to decreasing, or from in decreasing order, the first axis should explain the most amount of variance in your data as possible. Okay, so you keep, this is my last slide, you keep as many axes until you exceed some threshold. Okay? So some common thresholds are 90%, 95%, and 99%. And 99%. Okay? So what they're saying is that you want to keep as many axes up until you have 90% of the variance explained, 95%, or 99%. So those are some common measures you can use. Okay? So if we define, this is my last point, if we define S to be the total variance, Okay, so what you're doing is you're summing over every single singular value in your data set. Right, so, okay, right? So we define that. So the total number of axes to keep, which is k, is such that, almost done. I have my last point. So what you're going to do is you're going to keep incrementally increasing k, right? And dividing by the total variance up until it surpasses some threshold, okay? And this is what's known as the normalized percentage. So this is between 0 and 1, okay? So this would either be 0.9, 0.95, or 0.99, okay? So what you're going to do is you're going to figure out what the total variance of your data is by just summing over all the singular values. And then what you're going to do is you're going to keep incrementally adding singular values. So starting from the first one, and then you keep adding up until the point where you exceed some threshold. And whatever that threshold is, that's how many that's how many components you keep. So for example, if I had 4 principal axes, and once I pass to the 5th one, if I exceed 0.99 or whatever that is, then you just use 4 principal axes. And that would be the number of components you keep. Okay? And that's it. That is dimensionality reduction in a nutshell. Next week, we're going to cover anomaly detection, and we're going to cover evolutionary computing. So stuff in machine learning that you'd see, that you'd model in human nature. So self-organizing maps, genetic algorithms, particle form optimization, machine learning that you'd see being modeled in nature. Okay? Thanks, and I'll see you next week.